Now consider the relationship between work, transfers, and execution time. Suppose the processor takes tau time units to perform an operation. Thus, the time to perform just the compute operations is tau times the work, W. Next, let alpha be the amortized time to move one word of data between slow and fast memory. Alpha has units of time per word. Then, the time to execute Q transfers is alpha times L times Q. Now let's assume perfect overlap between data transfer and compute. Then the minimum time to execute the program would be the maximum of the time to compute and the time to move the data. Let's refactor this expression a little. This refactoring shows the execution time relative to the ideal running time, which is just tau times W. It's ideal in the sense that it assumes data movement is free. Now, relative to this ideal computation time, you need to pay a penalty. This communication or transfer penalty is the price you pay for having to move the data. Now, this penalty has some structure. Let's start with the denominator of this second argument. Why, it's nothing more than the algorithm's computational intensity. Recall that intensity has units of operations per word. Now, what about the numerator? The numerator is the time per word divided by the time per operation. It's a ratio of parameters that only depend on the machine. In the literature, it's sometimes referred to as the machine's balance point, or just machine balance. And just like intensity, it has units of operations per word. In other words, this ratio tells you how many operations can be executing in the time that it takes to move a word of data. Machine balance is kind of a special parameter, so let's replace it with a symbol, capital B. That's B as in Buzz. Okay, so what we have now is a general formula for the minimum possible execution time in terms of the balance of the machine and the intensity of the algorithm. For completeness, we could also estimate the maximum time for a computation in this model. It's basically the sum rather than the max. That's because if there's no overlap, you have to pay for computation and communication, one after the other. Okay, so we have a formula to estimate the minimum execution time. Sometimes, rather than asking about execution time, we'll ask about a certain measure of performance. I'll denote that measure by capital R. Its numerator is tau times W star. In other words, the best time in the pure RAM model. So what does dividing by T do? Why, it gives you the following formula. It says the best possible value of the normalized performance is W star over W times the min of 1 and intensity divided by balance. This measure of performance is inversely proportional to time. Therefore, higher values are better. Take a moment to ponder it as you'll explore it in more depth momentarily.